autoencoders. So this is a collaboration between myself and my colleague Hayden. So during the presentation, we're going to switch back and forth to talk about different parts of the project. So the central question that we're trying to answer is, can we use machine learning to detect cybersecurity events at scale? So at Adobe, we have 30,000 employees interacting with our internal software, generating 1.5 million logins per day. And so that big of a volume, it's difficult to scale, as you can imagine. So what we want to know is how to extract the most probable events that our analysts are interested in efficiently, but also how to better understand Adobe's employee login behavior. So the plan is to use machine learning to detect and understand anomalies, apply rules to anomalies for specific use cases that our analysts are interested in, and then return a prioritized list of anomalies for human review. And then also explore blending data sources. So Hayden's going to talk about feature engineering, and I'll be back to talk about modeling. Oh no, I have more time. Totally forgot about this stuff. Sorry. So we have about 1.5 million logins that come in. They get Okta's heuristic model. And because the data volume is so large, they have to control the look-back period for each user's like previous logins. So you go back up 20 to 50 logins. If you go too far, it's going to take too long. So it costs compute performance. So as a result, you can't really look long-term at people's behavior. So let's say Hayden goes to the beach 3 times a year, every year for 5 years. It can be a problem. It can get flagged as an alert when in reality it's not. It's just something that he does all the time. This leads to alerts that don't really need to go in front of the analyst, but end up having to. So there's too much in the cloud for the analyst to go through, and can lead to reviewer fatigue. So what we want to know is, can we put machine learning better that essentially filters out those logins and gives us anomalies from a model perspective that we can then apply a less complex heuristic to in order to get fewer anomalies for our analysts to look at, but they can get through quicker and hopefully find malicious activity faster. So Hayden is going to talk about feature engineering.
Yeah, so to kind of build on what Jericho was talking about, so kind of the primary issue relates to the fact that Okta and Enter ID kind of user behavior logs. They're mostly kind of rules-based, as Jericho was saying, and like they have some APIs, like Okta has the behaviors API, Enter ID has risky behaviors, which tracks some information, but it's normally not detailed enough. It doesn't have the look back that we require for the analysis that we do. So again, the goal is, hey, can we estimate the probability distribution of a user's login behavior? And if we can do that, then we can potentially predict an anomalous login, right? So if somebody logs in from something that's outside their latent space or their probability distribution of that user, we can hopefully predict it. That's the goal of this. And that especially is important because if you think of bad actors today, a lot of the threats that we see are much more dynamic. The ways that people steal credentials, the way that kind of just the threats that we kind of see are more emergent. So we need a model that can adjust and adapt to some of those dynamic behaviors. So how do we do that? Well, there's 2 primary things. The first is we want to build features that kind of establish something about the user's baseline, based on what we know. And then if we have that, we can start to encode violations alongside those baselines. So basically, you can think of it as we're trying to add as much detail to a log as it comes in through the pipe, right? Both baseline information and violations. And with all that information in place, the goal is that will give the model the ability to determine or distinguish the distribution of a user's login in terms of good logins or just normal ones versus anomalous ones. So how do we do that? Well, we start with what we know, right? So in this case, with users, we know a few things that come to us from Okta. So where a user lives, what device they might use, and we can encode that, right? So we'll kind of talk a little bit about some of the challenges or some of the things that we have to work through, but to start with, you can think of it as start with what we know, encode that, and then encode the violations associated with it, which is all kind of serving model kind of training later on. So let's talk a little bit about feature engineering. So one of the things that came up quickly is we deal with a lot of multi-dimensional features. And when I talk about that, like, that's kind of a solved problem, especially in deep learning. For example, if you have a sequence of, text in a string, you want to encode a sentence, for example, you can do that, right? You can tokenize it, create an embedding, and do some kind of transformation with that. However, what we're thinking about is more of a compression. So if you take a multi-dimensional attribute, let's say device. So device configuration can have multiple kind of features associated with it. You can have like IDs, you can have kind of the OS, client, things like that. So what we really want to do is compress that into a single dimension, because then that allows us to do analysis that kind of generates stronger baselines without noise. So that's what we start with. So we use something called the Z-curve. There's an example there. I don't know if this shows it, but yeah, it's an example code of just applying it to a device. In this case, a very simple example here, but a Z-curve is really nice because if you're not familiar with it, it's a Hilbert curve, and it's just a space-filling curve. The nice thing about it is it preserves locality. So what I mean by that is, if you have two devices, let's say Windows 95, Windows 98, and let's say they're multi-dimensional, and you compress them, the relationship of how close they are in the multi-dimensional space will be preserved after you compress them. So that's really valuable, because if we can preserve that locality, we can feed it into a model downstream and it's preserved, right? So again, that's the goal we want to take there. Another reason is noise, right? So as I mentioned before, a lot of our features are high dimensional. This is an example of latitude, longitude coordinates. And so if you do like a feature, or in this case, a frequency analysis of a user's logins based on latitude, longitude, it's too noisy, right? It's points on a map. So it's very difficult to kind of get an understanding of where a user kind of lives, where they logging in from. However, if we apply geohash, which is just a z-order curve applied to latitude and longitude coordinates, you can associate a precision. What the precision does basically creates a box around where the user lives. So it just kind of expands the range. But when you do that, the noise goes away. So you have a much tighter frequency that you can associate with that user's login. And again, that's valuable, because when we move, when we move on to creating baselines, that's what we want. So strong frequencies that we can relate to a user's logins. So kind of moving, well, in fact, so moving a little bit further there. So when I say frequency, I've kind of just been saying it out loud. What I really mean by that is, if you take like a measure, let's say geohash, like where someone logged in from. It's as simple as, if I just count the number of times somebody logs in from this location, and I divide it by the total number of logins, that's what I mean by frequency. So in this case, you can think of every feature of interest, whether it's device, anything like that, as when I talk about frequency, is that. Another way you can think of it is as a conditional probability distribution. So in this case, it's the probability of, if X is the number of times I log in, it's X given this location, or X given this application, or IP. So one thing I've talked about is, we have these frequencies, but they only represent a sample of the user's true behavior. So we need to adjust to account for the actual true population, or true frequency that represents a user's login. Now what I mean by that is, if somebody logs into an SSO gateway, it really only represents a fraction of their logins. So on average, we get something like 20 to 30 logins per user per day through the Okta SSO portal, but it's just a fraction of their total login behavior. So we need some way to estimate the ground truth. All the frequency is just a binomial distribution. So the Wilson score interval is just a simple measure that just says, hey, if I extended this out n many trials with using this frequency, what would the true frequency distribution be for this user and this feature, right? So that's what just shows up here. We do that correction, and we get a confidence interval, that we can associate with that frequency. And why is that useful? Well, we can do things with it, right? So on right here is the Wilson score interval here. And that's just, again, just a UDF. It's a very simple example, but it generates, in this case, a confidence interval, upper or lower. And then with that confidence interval, we can do something with it. So this is a simple example. There are lots of ways, but you can choose either the upper bound or lower bound. This example just uses the mean. And we can choose a threshold. You want to do that kind of statistically. But if you have a threshold, you can then determine, hey, is a frequency above or below it? If it's above it, you can include it in a user's baseline calculation. So again, what we've described so far, we've done some encoding. We've applied some threshold using kind of simple confidence intervals, using the Wilson score. That allows us to generate then a baseline set of tables. Now these are tables that we store in Databricks per feature. So if I have, for example, geohash, I can now have a table that I can just look up, and if I want to know, hey, what's a user's baseline location, I can go here. And I can then use that to enrich new logs coming in, right? And additionally, I can also catch violations that are associated with those logs. And those will be fed into the feature table. Cool. So we've kind of applied some of this encoding state, but as usual, the big problem with machine learning is the changing nature of encodings, right? That's the constant dilemma. So once you've applied encodings to a feature of interest, they're going to change, right? So at Adobe, right, we have a ton of employees. We're getting new ones all the time. People leave. So that encoding state or dimension is going to change all the time. So how do we capture that? Because the model is going to be trained on a certain encoding state that's going to change. So there are lots of ways you can manage encodings in Databricks. We're just going to talk about one way, some kind of suggestions. But one way that we did it at the time, and this is because feature, for example, you can use a feature store to build a table associated with a feature. At the time, we couldn't do it because it was restricted to using Hive Metastore. Now I think it's using Unity. So there's been some updates there, I think. But in this case, what we did is we used experiments. Let's see if I can move along. So what we did here, we had two approaches. The first is an experiment per user. And then this is where we started. So we had one experiment that we would create per user. We would basically calculate the encoding dimensions associated with each user, and then we'd have a model that would get trained per user. And that was the first approach. And obviously, at the time, our assumption was like, oh, maybe the user behavior changes, and we need to capture that in the model. And it turns out, no, it wasn't as big of an issue as we thought. It also didn't scale that well. We had 30,000 plus employees. So what we moved to instead is a single model instead. So we just added actor as a feature that gets included in the encoding dimension. So every time we do a training workflow, there's basically a pre-step where the encodings are calculated, they're pushed into an experiment, and then those are sent to, for training or anything like that. And the nice thing about the experiment is you can access it at any point in a workflow. So it just makes it kind of nice and pretty flexible with what we're trying to do. But again, there's lots of different ways to do it. That's just one. And this is an example of that and how we implemented it. So code here, this is just creating, and I kind of, don't get too much into it because it's a bit of code, but you have an ML context, which creates a run, and then we create just basically a JSON map that contains the encoding state. By that, I just mean the max encodings, right? Because you need to send that. If you want to create an embedding layer, for example, on a neural network, you're going to need that. So we do that, we log it, and then on the training side, in this case in PyTorch, you can just retrieve it. You just pull it out, pull the artifact back, and that gives you the encodings that you need. Cool. So again, that's kind of the steps to get us the initial pre-training we wanted. So again, we do some hashing, we do some correction using the normal distribution, apply some baselines, encode some violations, and we feed all these things into the model. I'm going to highlight 2 points, and then I'll hand it to Jericho. The first thing I want to highlight is, this is a recommendation we just learned through trial and error, is to version your encodings. So you're going to have a set of encodings for the features you care about. My recommendation is version, because there will be drift and changes, and you want some way to explain those changes over time, because they can be due to one feature, right? So we had simple situations where you can get a flood of nulls from something upstream that happens that maybe corrupts the logs further down, so you may not want to train on that. So again, if you can version things, it makes it easier to go back. Again, here's the final features. This is not comprehensive, but it's at least a list of some of the things we use today. Actor ID, some of the baseline fields, login event, some event details, etc. And this kind of leads us to the workflow. Again, this is a simpler example of what we have, but it gives an idea of how it works. So on the left, we have the freeze actor portion. This is what I was talking about before. Some of the features change frequently. So you actually may need to freeze them to prevent anything changing during training, because that can happen. Then we do the encoding step, which we talked about before. The frequency analysis is just applying the Wilson score to the features of interest that we need to correct for the population. And then finally, we create the training data and validation and move on to our training step. So I'll pass it over to Jericho.
So we have So we have a lot of things to consider with what approach we're going to use. The typical culprits here: heuristic models, supervised models, and unsupervised models. We've already talked about some of those limitations for using a different kind of heuristic model. Difficult to maintain for all use cases, look-back restrictions, difficult to scale. The other thing is blending the data sources. So we have a lot of different cybersecurity data sources that we can use to get a more holistic picture of an actor's behavior. But if we have to maintain rules for every single data source that we use, it can get kind of out of hand. Another big one is it's difficult to discover new edge cases and anomaly types. So once you apply a set of rules to your data, anything that's unknown that maybe you didn't characterize with your rules, it's just gone, right? So we could use supervised models, and that solves a lot of these issues, but we require labels. We don't have anything organic to use, so we have to generate them. Then we have to use rules to get heuristic models. And so we introduced the same problems we had to start with. So naturally, we looked on supervised models. We don't need labels. We don't have look-back restrictions. We can easily blend them into data sources. They're easy to maintain, and they can reveal unexpected patterns. So think about where that autoencoder layer or unsupervised layer would be. We're calling that sort of raw anomalies, what the model thinks are anomalies. And then we can just apply these very easy heuristics that the analyst want to quickly look at. And we can go back and look at anything else that had high loss that maybe didn't fit into that rule. They don't just go away. So we use an autoencoder. And so I know a lot of you are probably familiar with it. I'll just kind of give a real high-level overview of how it works. But essentially, it's a neural network. Unlike typical neural networks where you have an input layer of a certain dimension and your hidden layers are of a higher dimension, and then your output layers, whatever dimension you need for your task. An autoencoder actually has hidden layers that have fewer dimensions, so it sort of compresses the data in what's called an encoder model. So the encoder model learns the data in an abstract representation that's called sometimes encoder representation, latency representation, and then the decoder model reconstructs that input from that latency representation. So if there is no anomaly, then it's going to get a near perfect reconstruction, and then when you compare the output, which is the reconstructed input, with the original input, you're going to have a very small loss. But if there is an anomaly in there, it's going to fail to learn it, right? It's a rare event. So the decoder is not going to be successful at reconstructing that anomaly, and it's going to tend towards something that's more typical of the user's behavior. So when you go to compare that reconstructed input to the original input, it's not going to match, and you're going to have a high loss. Now, the feature engineering Hayden talked about is designed so that we minimize any historically missed anomalies from being in our data set, because we want the training to have the smallest loss possible, so that when we're in production or whatever, an anomaly comes in, it has a high loss. So once we train the model, we get the standard deviation across all samples and an average standard deviation, and we store that in a flow. So then we move to something, the validation step, which is a little different than how normal validation steps are, but I'm going to walk you through it for a single actor. We actually do this all at once, but it's kind of muddled to put it all in one workflow. So we have validation sets for every actor that we isolate from the training set, and then we talk to our analysts, see what use cases they're interested in. We'll talk about one in a minute called possible travel. And we design injections around that, inject it into our validation sets, score it with the model that's already trained, and then if we order for high to low loss on all the samples, we expect to see those injections at the top. And that's what we do see. And so we load that standard deviation from our training, the average standard deviation, and we compute z-scores for all the samples, and we choose a threshold that captures all the injections that we made. And so one of the use cases that that our analysts are interested in is called impossible travel. So impossible travel just means a user logging from one geohash and then another, and not enough time passed to reasonably get from that point, from geohash A to geohash B. So how we define that is we just say, we compute a effective velocity, so the change in distance between the geohashes divided by the change in login times, and we just compare it with the speed of a commercial airplane. We figure that's a pretty conservative way to do it because it doesn't account for waiting in line, planes don't fly in straight lines. So if somebody's effective velocity is greater than that, then somebody will look at it. And so we create a hierarchy of injections, everything from geohash changes with reasonable times of travel, unreasonable times of travel, no geohash change, normal login times, like maybe somebody logs in at 3 a.m. and normally don't. And we started with just a small set, 100 users, and we sprinkled 18 of these injected anomalies throughout those 100 users. So some users had them, some users didn't. And we just wanted to see, could we recover? And we were able to recover 17 of the 18, but the one we missed ended up being a service user, which is actually software tied to a user account. So it behaves strangely, but not like human. It has a really broad spectrum of login times. So then we scaled it up. We looked at it for 30,000 users. So we repeated this process. This is just 7 of 30,000. But you can see we have the injections are the true positives, and the non-anomalous stuff, the normal stuff is the true negatives. And we compute z-scores, user-specific for each user, and we attempt to recover. And we're able to get really good F1 scores. I mean, these are the top ones, because this is at the top. But average across all of them is about 98%. But again, when we look at what's dragging us down, it's just service user accounts. So it's one thing we built a really great way to detect service user accounts. And so now that we have a user-specific z-score threshold for each user, we have that average standard deviation for training, and we have a model. We can just put that into production, and if Hayden logs in, he'll go through his login will go through the feature engineering layer, it'll get scored by the model, we'll pull up his z-score, compare it, if it's above, we pass it on to an analyst. But we preserve that sort of raw anomalous layer that comes out of the autoencoder. So if we see other things that have high loss that aren't characterized necessarily by our heuristic, we can go look at it, try to figure out what's going on, and discover new edge cases. And Hayden's going to talk more about that now. Right.
Yeah. Before I actually jump to talking about just the anomalies and some interesting takeaways that we have there, because there are some interesting ones, and networking stuff is very complex. It's going to be a large narrative here going to repeat. But I wanted to highlight some pain points or lessons learned using PyTorch, training and inference. One thing that's big, this is probably going to seem obvious to many of you, but when you use PyTorch, just test on the CPU as much as possible before you move to CUDA. What you will end up getting is you'll get the dreaded CUDA assertion error. And at that point you know you're in trouble. Because that basically tells you nothing about what went wrong. So you'll run into that. And so to avoid it as much as possible, and it can happen for any reason. It can be a bad data point. It can be, some type of an embedding layer went wrong. It can be so many things. So using the CPU will help you immensely. Additionally, this is something that, again, we highly recommend. Use Parquet tables if you're storing large vectors of data, especially tensors. rather than delta. We found that when we use delta to do it, there's just a high overhead cost that gets kind of computed in to the size of the table, versus if we just push the vectors for training, validation, and inference directly into a separate parquet store, it's just much better, much faster, smaller, everything there. And you can do that in a variety of places. You can use DBFS or an external volume or just our location, wherever you want to do. There's also a library called Penstorm that we use. We've kind of gone back and forth on it. It helps with larger data sets, but the underlying logic behind it is using basically PyArrow. That's a good library, but it doesn't scale, especially if you get into like hundreds of millions of records. So we ended up just rolling our own data set, basically custom data set with PyTorch. And it's an iterable data set, if you're familiar with it, that's the class we used, and just streamed it in that way. One other mention I'll make, just at kind of in the interest of time. For inference, one thing I will note is you can use multiprocessing on the CPU side along with training on a GPU. It's risky, but in our case that's actually very important because we have multiple actors we need to score at once. But you can do it. You just have to make sure the memory for the GPU, you understand what the lift is going to be, how much you can scale, etc. So, yeah. Let me just talk a little bit about anomalies found. I mean, we can't talk about all of them, but we've caught quite a few interesting things. One of them I'll highlight if we can is session hijacking. So we had a situation of user A has a session in one location. They take that session and log in from a completely different location in a small window of time. So our model caught that. What's kind of more interesting that's been, again, I think a real win, are the discussions of more of the edge cases, the interesting things. So I'll go over a few of them, but essentially, let me actually start here. I'll go right here. Let me just start it by talking about some interesting things that qualify for impossible travel, but they're not anomalous. But some of them are kind of funny or just kind of weird. Others are actually valuable insights that are driving policy change at Adobe. So one of them I'll mention, and you can kind of think about this if you just think about how devices stuff and all the devices we use today. Every mobile phone has a roaming IP, right? And I'm sure you're all familiar, but a roaming IP is typically associated with your home location. And the reason they do that is so your ISP can charge you or throttle you. Right? They don't want you to escape, right? So they'll throttle you based on your home location. So it's very likely, in fact, we've seen this where somebody will be on vacation and they will be on their computer, one thing, logging into Adobe, and then on their other, they'll be on 5G on their mobile device, and their roaming IP will connect to their home location. So that will register as an impossible travel anomaly. It's not anomalous in this case. In that particular case, we can handle that by just, again, recognizing that there's usually a certain set of IPs associated with a person's home network. You can kind of associate things that way using a baseline. A second thing we'll note is you can have issues where the WAF providers get it wrong. We had an issue where Cloudflare, basically we had a user that they flagged an anomaly on our side. They had 2 logins. They were registering a device. One login was from their home location. Another one was from an anomalous location, but the IP address was the same. And it turns out the reason for that was Cloudflare, the WAF provider, had, for whatever reason, had just a hallucination, I guess, I don't know what you call it, and just assigned a different location for that login. So again, that's a good sign, like our model's very precise, but it can tell you that things can happen outside your control that can affect the model's behavior and what it knows, right? Because it can only know and rely on the data it has. One way that we accommodate that now is we use weights, essentially, against the features, so that way, if there are issues with something like GeoHash, it allows for more a combination of different effects that help contribute and flag a higher level anomaly. One other note I'll make about things that are in policy change. So this is something that can happen with SSO applications. Okta allows this. You can have proxies within SSO environments, unfortunately. Some of them are good, but the downside with this is we've seen a rise in basically third-party proxies that are set up. They're not necessarily owned by Adobe, they can be contractors. And essentially what happens is you have a set of users that are all different locations. They'll log into this proxy, and then they'll use that to log into Okta. And that's a risk. So that's led to conversation internally about, I mean, we need a policy for this. How can we better track it? What's acceptable, what's not? Things of that nature. And this kind of goes back to what I was talking about at the beginning, dynamic behaviors, right? So network edge stuff is extremely complicated. And this is something that we couldn't have really found on our own. Like maybe if somebody was pouring through the logs and just was really bored, but like having a model just reveal that and just kind of show that to you, I mean, that's really the win. It's filtering through that noise, showing you stuff that's interesting that you can kind of take advantage of. And that's also led us to think about what we want to do in the future. So in this particular case, we mentioned that we're starting to get kind of sub-classifications off of these initial anomalies. And so one thing that's kind of come up and that we're thinking about now is it possible for us to create a light classification layer on top of the impossible travel anomaly definition that we have? And these would be tighter, kind of more focused definitions around impossible travel and the edge cases that we're starting to see. And this could just be associated as another step in the Databricks workflow that we have. It also would allow us to more focus again, if we can classify them quickly, it also allows us to start to realize, hey, what's the velocity? How many of them are we seeing? Is there one that's maybe more, we should prioritize more than another? As far as other things, I mean, there's going to be other unsupervised detection approaches. I mean, one thing that could come out of this for the classification is even semi-supervised, right? If we're able to determine some labeling and stuff like that, that could easily feed into a semi-supervised approach. Also, we're blending multiple sources. That's essentially the plan. So the plan is to have basically Okta and Azure go through the same essential workflow. Azure is obviously different. It encompasses different aspects of SSO. The goal is to centralize them for users to utilize. And with that, that's it. That's our main presentation. We'll just move to questions and question and answer. Yes?
When you did the initial training, did you intentionally attempt to remove any anomalies that you knew of, or did you not worry about it because you figured that the autoencoder decoder session would get a good gestalt anyway of what's normal behavior?
We removed all that we could.
Okay, right, of course. Because you don't know what you don't know.
Yes, exactly. There are still unknown unknowns. But you just have to take into effect, like, again, the volume of data we have, hopefully will annul that during training. But yeah, it's a good point. Yes?
Yeah, so my question is like, how do you ingest the data? Like, let's say you train your model right now, and after a month you'll be having like tons of data. So how do you streamline the live data into the model again and deploy it? Like, is there any pipeline?
Yes, that's a great question. So we have, again, two workflows. One of them is training that runs on just a cadence. Usually it's weekly or something like that. And in that process, we go through the whole thing again. So we sample, create a training and validation set. The model gets trained off of that, kind of with the logic Jericho was talking about. And then we stream the data in for inference. So it's effectively data is streamed in. We have kind of a batch process that runs on the stream data every hour for inference, but it could be streamed. At this point, it's just that. So, but yeah, that's the process now. So it's scored hourly.
This was a great presentation. And when you calculate the total loss, do you assign different, is it a hyperparameter that you assign into certain weights to different losses over there, or is it learned through the network itself?
I missed the first part. So what was the hyperparameter you asked about?
So when you are calculating the total loss there,
Total loss.
right, so there are different losses and then you combine
The
them.
z-scores and stuff like that. So you're asking if that's a hyperparameter we tune in terms of...
Is it hyperparameter or it gets learned by the network itself?
Yeah, I think so. There's a z-score that we kind of
You're asking if we, I'm sorry, I thought, did you say something about weights on the logs? Is that what you, or you're just, we don't tune the z-score, it's just something we calculate from the validation set.
Thank you.
Can you talk a little bit about the user logging? So when we are gathering that data, are you looking more at frequency interval over an hour, over a week? How do you decide based on the features, what is the exact parameter to choose from?
So is the question kind of what features to choose for the frequency distribution? That good question. I mean, it's a combination of just talking to SOC analysts in our case, and also just it's almost similar to like just a variance. What are the features that don't have extremely high variance that we think that if we can kind of decompose or decompress, essentially that they'll have kind of good representations associated with the user. So it's a little bit of experimentation, it's a terrible answer, but experimentation, talking to experts, and kind of just trying things out. That's how we came to the features that we use.
And what is the usual data set size?
And for us, I mean, it can be, the log data can vary, but I would say it's on the order of, I'd say, hundreds of gigs of data. So there's system log data that we deal with probably weekly, let's say. So I'd say probably 50 gigs a day.
And the weekly job that runs, which is doing training, is that also over the entire set of data or like most recent data?
Yeah, it's over everything. So essentially what we do is when we build the training and validation sets, we sample from the entire, I mean, it's too big to run it against everything. So we just create a representative sample for training validation, and then that gets fed into the model for training.
Thank you.
So with that answer, do you have any weight or any noticing differences with newer, with time going on, right? Time is a thing that happens, things change over time. Do you respect more recent data is more important or not, or see any drift at all due to time?
That's a good question. I would say overall, honestly, beyond just the scenarios that we're starting to uncover, the overall behavior hasn't changed that much, which is surprising. There have been obviously things within coding state that change, but overall, it's actually been pretty consistent. So the validation set helps us, like we talked about, we have a table to help track metrics, especially like a z-score for a user was to drift. Suddenly that might tell us maybe something's off. But like Jericho was saying, our F1 threshold has been pretty consistent at 98%. And even our mins on that are pretty, it was like 87%, something like that. So as far as now, it's held pretty steady, but it's, you still have to evaluate.
Thank you, by the way, this is really fun. Thinking about that things change over time, and it's cool, it's unexpected that things would still work and still be stable. But thinking about, how to identify anomalies, right? I have someone who moves every month for the last 2 years. Is the chance of something anomalous happening on their account more likely for me to miss? Like, the model of representation is going to learn, is that going to be more forgiving for that particular user? And then if something happened with them, am I less likely to catch it? I don't know what your thoughts on that.
So you said they move every month, is that?
Sure, yeah.
So I think that might be problematic, but I think once they've established that they've been there for at least a month, it might get flagged in the beginning, but eventually that would be it would become part of the baseline.
Yeah, one thing I would note, for impossible travel, the definition is not only that it changed location, but that there's like a velocity change associated with that login or other features of interest. So we do actually see users that will move frequently. We have some that are just, they're transient, I suppose. But what I would just say is we're able to catch that. We're able to kind of know some of the changes there, but like Jericho said, that's something we'll